salt will initially fill the voids, reduce the penetration of acidic acid into the concrete, and reduce the deterioration of the concrete. But eventually, the acid will influence, will react with the cement paste exposed to the surface, attack a calcium hydroxide and calcium silicate hydrates. So eventually, it will lead to the disintegration of the concrete. So this is the graph here. It's actually concrete affected by hydrochloric acid. You can see that the surface cement paste are all gone. So what you see is the coarse aggregate exposed. Come back to this table here. So what you see actually when we're dealing with this group of acids, so the salt forms, it's soluble. Okay? So when we're dealing with the phosphoric acid and tartaric acid, and in this situation, the salt forms are insoluble. Right? So depending on whether the salt form is soluble, insoluble, expensive, so they affect the concrete in different scale. In principle, when we talk about the corrosion of concrete exposed to acidic environment, as we talk about these two chemical reactions, the acid actually attacks cement paste. However, in real life, it has been observed that depending on what type of the aggregate used in the concrete, it also has some effect on the durability of the concrete. What has been observed in research is that limestone and dolomite aggregates are also subject to the acid attack. So therefore, in principle, if you are dealing with strong acids, Portland cemented concrete is not a good candidate. So in the last class, I will talk about if we are dealing with the chemical plants where we know we have a low water to cement ratio, what do we have? Okay, so basically we use polymer. So next one I want to talk about, it is related to the acid attack of the concrete. So this is actually corrosion of a sewage pipe. So in cities, okay, so from the buildings to the large sewage pipe, so you see this concrete sewage pipe, right? So when the concrete is used for sewage pipe, so in this case, you see that you have a sewage here, right? And typically domestic sewage itself, it's usually not a problem. It is the acid generated, okay, from the sulfur compound in this sewage. Okay. So the thing is, when you have a sewage here, domestic sewage, inside this sewage effluent, you have some sulfur compound. So under the influence of anaerobic bacteria, so it can reduce this sulfur compound into H2S gas. Okay. So when the gas forms, it goes up. So this part, it's not filled with the sewage. So when you have this H2 gas is formed, it will be dissolved in this water film, okay, around this sewage pipe. And in the effect of aerobic bacteria, so it will oxidize this H2S, okay, dissolved in this water film. So it produces sulfuric acid. So therefore, in this part, you have actually sulfuric acid, which will be attacking the concrete. Okay? So during the service life of this sewage pipe. So we know that sulfuric acid is fairly strong acid, right? So it attacks the concrete. Not only it destroys the hydration products, and it can also cause expansion. So therefore, in many situations, you can see this, you have the upper parts, okay, where you have severe deterioration of the concrete sewage pipe due to the sulfuric acid attack. And oftentimes, this part, the deterioration is more severe compared to the part covered with the sewage. So this is actually a picture showing that the sewage pipe by the chemical attack, mainly sulfuric acid. You can see all these concrete are deteriorated. So when we talk about this deterioration of sewage pipe due to the attack of the sulfuric acid, so in principle, this is also affected the cement paste, right? However, the experience or the observation for the real life also indicate that aggregate also has some influence on the deterioration of sewage pipe. It has been observed in real life is that if the concrete made with the limestone, then the service life of the concrete is greater than the concrete made with siliceous aggregates. So how do we actually protect the concrete in these sewage pipes from the sulfuric acid attack? So basically one thing is coating. Okay? So you can use different organic things. For example, you can use epoxy to coat the mortar. Also, you can use bitumens, also resins to coat the sewage pipe. And the other thing actually, the research shows that if you're making the sewage pipe, not using Portland cement, but using calcium aluminum cement, and then resistance to the sulfuric acid, it's better. So the calcium aluminum cement, the coverage is beyond this class, so I will not talk about this one. So in addition to these coatings, the other thing which has been used traditionally for treating these concrete sewage pipe is to using sodium silicate or the so-called water glass. So basically you coat these concrete sewage pipe, and these sodium silicate can penetrate into the concrete through the capillary pores. So with the protection of this water glass on the surface, so it can extend the service life of sewage pipe made of concrete. So these are talking about the small sewage pipe, which can be easily replaced if it's deteriorated. So for large city, for example, Singapore, we have deep tunnel sewage, right? So for the last part, people typically use lining. So for example, lining of the PVC sheet. So therefore, the sewage does not in direct contact with the water. Okay? Because the thing is, we're talking about the concrete does not tolerate acidic environment well. Okay. Okay, early today, Dr. Kim talked about alkali silica reaction. He also mentioned that when we talk about alkaline aggregate reaction, the other one is actually called alkaline carbonate reaction. So when we talk about the alkaline carbonate reactions, and when we're dealing with the aggregates made with a dolomitic limestone, okay, with some clay in it, and then when you're dealing with this kind of the aggregates, it can cause alkaline aggregate reaction. Whereas for the alkali silica reaction, its aggregate involves some reactive silica. So the real mechanism of the reaction of alkaline carbonate reaction are still not well understood. But the thing has been observed in real life is that the crack pattern of the alkaline carbonate reaction is very similar to those of the crack pattern caused by alkaline silica reaction. So in principle, this is current understanding that when we're dealing with a dolomitic limestone aggregate, the reaction involves the reaction of dolomitic limestone react with sodium hydroxide or potassium hydroxide from cement hydration inside the concrete. It will form magnesium hydroxide and calcium carbonate and sodium carbonate. This sodium carbonate itself is soluble. So this can react with the calcium hydroxide from cement hydration and to form sodium hydroxide and calcium hydroxide. So this sodium hydroxide supply the sodium hydroxide, so it can continue take this dolomitic limestone. So it is believed this chemical reaction will cause expansion, so eventually cause internal stress and cracking of concrete. So in the situation when we're dealing with the dolomitic limestone type of the alkaline aggregate reactions, water is actually a main component which are essential for the expansion, similar to the situation when you're dealing with alkali silica reaction. So one thing different from alkali silica reaction, Dr. Kim mentioned one of the things we can actually reduce the alkali silica reaction is using some supplementary cementing material, such as fly ash or slag, that can help to reduce the alkali silica reaction. But in the case of alkali carbonate reaction, the pozzolanic materials are not effective in controlling the alkaline aggregate reaction. So in the situation when you're dealing with the dolomitic limestone, and in this case, if you have to consider the potential alkaline carbonate reaction, so one thing is actually to control the alkaline contents in the cement. So one thing I want to mention here in Singapore. So years ago, many years ago, most of the aggregates used for construction coming from Indonesia and Malaysia. So the source is actually fairly, fixed. So we know the aggregate better. So any of you know that a few years ago, Indonesia banned the export of sand to Singapore. So from that time, and the Singapore construction site, the aggregate actually coming from many different countries. So one thing is that when you import aggregate from different countries, the quality control is very important. One of the concerns is the long-term durability. So one thing is the alkaline aggregate reaction. So although Dr. Kim mentioned early on, so we have different test methods which can be used to evaluate whether the aggregate has potential alkaline aggregate reaction. But the thing is that in order to make sure, okay, so what if you have these tests which at the time didn't detect the potential alkaline aggregate reaction? So what if in this situation, so if we can use low alkaline cement, then even the aggregate is reactive, then we should not have a serious problem of alkaline aggregate reaction. So because of that, currently most of the cement used in Singapore are actually low alkaline cement. So mostly it's consideration of potential alkaline reaction, alkaline aggregate reaction. The other thing is actually, in principle, if you have this kind of concern, you should avoid susceptible aggregates. But as Dr. Kim mentioned early on, the aggregate occupies about 60 to 80% of the volume of a concrete. Oftentimes it's expensive, so if this is the area, okay, so the aggregate you have, it's reactive. So if you say, I don't want to use it, if everything has to be transported from other locations, it becomes very expensive. So therefore, sometimes people do use good aggregate and mixed with the so-called problem aggregate. So diluting the reactive aggregate with less susceptible. Okay? So this is in addition to the alkaline silica reaction we talked about. So I just want to briefly mention this alkaline aggregate reaction. Okay. okay, most of the concrete, in reinforced concrete structures, okay, most of the durability problem, actually one of the most significant durability problem in reinforced concrete structure, it's not the deterioration of a concrete itself, it is actually corrosion of steel reinforcements. So basically around the world, every year, billions of dollars of money has been used to repair the concrete due to the deterioration of steel reinforcements in reinforced concrete structures. So the thing is that when we're dealing with the durability of a concrete, for example, when we're dealing with the sulfate attack and acid attack and alkaline aggregate reaction, these are actually related to the concrete. But when we talk about the corrosion of steel reinforcements, so initially it's not a problem of a concrete. It's a corrosion of steel. It's a steel problem. But the thing is, when the steel corrodes, and then it affects the concrete, then it becomes the problem of a concrete. Right. So I will talk about this corrosion of steel reinforcement in reinforced concrete structures. So here are two pictures. So this one is a structure exposed to marine environments. So in the marine environment, you have seawater, you have a chloride, right? So the chloride, when the chloride penetrates into the concrete through the capillary pores. So in the vicinity of steel reinforcing bars, if the concentration of the chloride reaches a certain level, if other conditions are satisfactory, then you can have a corrosion of steel reinforcements. Okay, so this is the one seawater. The other thing is actually in Singapore here, we are fairly comfortable. Every day it's 30 degrees Celsius. But the thing is that in a certain country, wintertime its temperature is 0 and below 0. So the thing is that in order to drive on highway, you need to, in order to drive on highway, let's say 100 kilometers per hour, you need to actually melt the ice and the snow, right? So in North America, winter times, if you have a snow or you have ice, the salt truck comes on the road, so they spray the salt on the roads. And this salt melts the ice and the snow, okay? So the thing is actually you have full of salt water, okay? So this is actually a bridge. So when you drive, you have a salt water. When you drive and the salt water are splashed, okay, to the sides. So this is on the side of a bridge. You can see that because of this salt water, okay, splashed to the concrete, the chloride penetrated into the concrete and cause corrosion. Okay, so this is another form of corrosion. And this is also caused by the chloride, but it's due to, they call the de-icing salts. I mentioned in previous class that for reinforced concrete structures, concrete is brittle material, have a low tensile strength, but has reasonably good compressive strength. So in reinforced concrete structures, concrete can carry some compressive loads, right? The other thing is that in reinforced concrete structure, concrete actually can protect the steel from corrosion. That's the second function. Concrete can protect the steel from corrosion. So the reason is actually related to the high pH value of a pore solution. So in high alkaline environments, high pH of pore solution, in this kind of situation, when you have a steel bars embedded in concrete, in reinforced concrete structures, on the surface of steel reinforcing bar, there is film called passive film. Okay, so there's a thin oxide film, passive film, formed on the surface of steel reinforcing bars at high alkaline environments. And this oxide film on the steel reinforcing bars, it is impermeable, and it's strongly adhered to the steel reinforcing bars. And the third thing is that because of this passive film on the steel reinforcing glass, it makes steel passive to corrosion. So therefore, metallic iron will not corrode under the protection of this passive film. So therefore, concrete can protect the steel reinforcement due to its high pH level. Under high pH level, you have this passive film formed on the surface of steel reinforcements. The question is at which conditions this passive film can be destroyed or can be damaged. Okay, so basically two things in real life can damage or destroy this passive film on the surface of steel reinforcing glass embedded in concrete. One thing I already mentioned is chloride iron, whether it's due to the seawater, chloride in seawater or de-icing salt. The other thing is actually due to the carbonation of the concrete, which reduces the pH level of a pore solution. Let's first consider the carbonation. So we talked about in previous class that one of the main hydration products in the concrete is calcium hydroxide, right? So when the concrete is exposed to the environment, the CO2 in the air can penetrate into the concrete to react with the calcium hydroxide to form calcium carbonate, right? So depending on the locations, if you in rural area, the concentration of CO2 in the air is fairly low, 0.03%. So if you are dealing with urban center where you have a lot of cars, etc., so the concentration of CO2 is fairly high. You can have 0.3% on the average. So the CO2 reacts with the calcium hydroxide to form the calcium carbonate. Right? So we talked about early on, the pore solution of the concrete typically is 13 or sometimes it's greater than 13. So when you're dealing with saturated calcium hydroxide, pH is greater than 12.5. And plus we have some potassium hydroxide and sodium hydroxide. So in pore solution, oftentimes you have a pH greater than 13. Due to the reaction of calcium hydroxide and CO2, you have a calcium carbonate. So because of these reactions, the pH will be reduced to 9. So with the reduction of pH level in pore solution, the passive film on the surface of steel reinforcing glass will be damaged. So before the pH is reduced to 9, when the pH is reduced to a level about 11.5, the passive film on the surface of steel reinforcing glass will be destroyed. So when the surface, this passive film is destroyed, if other conditions are satisfactory, then the corrosion can be initiated and propagated. So I will talk about what are the other conditions necessary for the corrosion. So the corrosion, the carbonation depth can be estimated using this formula. So D here is depth of a carbonation, and T here is the time. So K here is parameter, which is affected by the concrete. So K here is related to the permeability of the concrete. So if you have a high permeability, and then the CO2 in the air can easily penetrate into the concrete, right? So the depth of a carbonation will increase with the time more quickly compared with a concrete with a low permeability. The other thing which affects the depth of which affects this K is the cement type. Okay, so when we think about the two things, one thing is Portland cement, and the other one is blended cement. So in blended cement, you have a pozzolanic reaction. So your calcium hydroxide content in concrete made with a blended cement will be actually less compared with a concrete made with a Portland cement concrete, right? So if you have a Portland cement concrete and the CO2 penetrate into the concrete, it will be reacted with this one. When all these calcium hydroxide on the surface is reacted, then it will, the depth of carbonation will increase, right? So the CO2 goes in. But when